Hi everyone, welcome to our November episode of GoingNative. My name is Gabriel Ha. I'm here with Steve Carroll, and happy Thanksgiving for those of you who are watching this around that time. So the big news for November, as far as Visual Studio is concerned,
if not the world.
Yes, if not the world, is the release of a whole bunch of awesome things earlier this month on Wednesday, November 12th, not the least of which is Visual Studio 2015 Preview. So for those of you who have been following the VC++ Bytes subseries of GoingNative, all those refactoring features, the productivity things, you can play around with those. I also want to give a special shout out to cross-platform mobile development tools, which is pretty awesome. It's something that our customers have been wanting, and you can go check it out for yourselves. So I'm going to kick it over to Steve, who will be introducing today's segment.
All right, cool. Today's episode is another of our series of ones about like sort of the future of C++, where things are going. Our team is lucky enough to have several members of the ISO-CPP committee, like Herb and Artur, who we talked to in our last episode. And today we're talking to Gabriel Dos Reis, who is a member of the committee, and he's going to walk us through all of the exciting things that happened at the most recent meeting of the C++ committee. We're here today with Gabriel Dos Reis, who is a member of the C++ team, but also a member of the C++ Standards Committee.
I'm Gabriel Dos Reis, dev on the Microsoft Visual Studio C++ team. I represent Microsoft in the Standards Committee. I'm also chair of the study group of undefined and unspecified behavior, things you don't want to know about.
Maybe someday.
Yes. And I'm happy here to tell you about what happened at last Standards meeting.
Okay, so you guys just spent a week in sunny Urbana, Illinois, where you guys all got together to talk about the future C++. What was special about this meeting?
Well, it was really a very nice meeting. 6 days in a row. You know, we start from at 9 and have long evening sessions. And the good thing about it is this is the first standards meeting after C++ 14 was released, so we could openly talk about C++ 17. And as a matter of fact, we asked Herb to ask ISO to request a new work item for C++ 17. So that's what we expect it to be.
So C++ 17 is the what people can look forward to is the next version.
Next version of C++.
And so you guys have three years
of release, and we are very happy about S plus 17, 14, 17, and hopefully 21.
Great. What I'd like to do today is make sure that people get a sense of what's coming for them in C++ 17. So let's start with the language things that were added to the language in this meeting.
Well, Steve, there are two things, the core language. There were additions and removal.
Okay,
and
let's start with new cool things.
Yes, it doesn't happen quite often that we'll remove things from C++, but this time it happened. So the coolest thing is that now you can write more generalized constant expressions as template arguments.
Okay, I'm going to definitely need to see an example of that one.
So what is a template argument? So usually in C++, when you have a template, you have a parameter, right? Here you can put a type or you can put a constant, parameter for a constant. So imagine here that you want to have an integer n, and you're parameterizing some class s. Okay, so you can instantiate this class with 2. It works, or you can have more, complicated expressions like s of 42 minus 3, and it will work. Now, the compiler usually represents these constants symbolically. So you can't actually have arbitrary integer expression here. What happens at the standards meeting is that we have a way to put more general expression, constant expressions that can be represented symbolically.
Loosening up the number of different ways you can express an expression in there?
Exactly. So here I put an integer just to introduce the notion of non-type template parameter. But imagine that is actually a pointer. So here I have a class s that is parameterized by a pointer to an integer. Now remember, the compiler is doing this at compile time. It has no notion of the actual address of the object, so it has to represent.
Been instantiated.
Yes, it has to represent this symbolically. So if you have at global scope an integer, let's say I, then you can take its address, and the compiler would pretend it is a constant because it is a global object. So you can represents you can instantiate the class S with the address of the object S. Now imagine you have an array, 4 elements. Well, the array is also at global scope. It has a constant address, but in C++, doing pointer arithmetic is very complicated. We don't actually allow you to say address of array of 2, because that will involve some pointer arithmetic, and we don't know how to do that.
Whereas address of A is already allowed?
Yes, allowed. Okay. It will be addressed to an array of
Got it.
4 elements. Now, imagine that you happen to have a struct A, and here you have a static data member X. And here, so you need to provide a definition for it, right? A colon X. Well, we allow you to actually write something like this. Take the address of this object.
Okay. Why would you want to do this?
What you want to do is you don't want to store the address in the program, but you want to use it as a part of the type, because what happens is that when you instantiate a template gets instantiated only when they are used. So if you're looking for ways to remove unused code, you would like to pass all these global objects as parameters to some templates, and the compiler would ensure that only things that are used are actually part of the code.
So it's about reducing the amount of code size.
Yes,
that gets
exactly. To
the minimal
and
set.
This is an example of places where templates are used to reduce code bloat, because usually people say, oh, template, actually you can use template to reduce code bloat, and this has been used in practice. So this works for these simple objects, but you can imagine you have another complicated class, then you can actually take the address of a sub-object and work the same. That's what we try to do with the core language. So the next feature we got into C++ 17 is nested namespaces. Imagine you're writing codes and you have several namespaces. They are nested. It's a namespace A. Then you have namespace B. So imagine this is std, and here you have some detail in there. And then go on. That's kind of cumbersome to write. So what C++ 17 allows you to do is you can just write namespace A : B and be done with it. And this reduces clutter. It's much simpler to read and it's much simpler to write. And this is a very good thing.
And think of all of the tabs and/or spaces that you may have saved.
Then, yeah, instead of having a staircase code, you just have the code right there and done with it.
Great. All right, let's talk about things that got removed.
Things that got removed. It doesn't happen very often.
Simplifying your life.
Yes, and I love this one. Trigraph.
What is a trigraph? I have no idea what a trigraph is.
Well, Steve, to be honest, very few people know what trigraph is. And if you know what trigraph is, you have been reading the Sutter for too much.
I feel better about myself now.
Okay, good.
Yeah,
I don't know all the rules, and to be clear.
Ha, I caught you.
So what are trigraphs? So essentially, it is a mechanism to allow certain non-ASCII keyboard to use to write C++ code. So if you happen to use these keyboard or systems where you cannot write hash include vector in your code, then C++ allows you to replace this hash with question mark equal. So here you have 3 characters that stand for just one character. And this is, this has been part of C and C++ for a very long period of time. Very few people know about it. And the trouble is that it does cause pain and surprises. Question mark slash. This turns into backslash. Now imagine you have a comment and you're writing some comments, say, well, what is this? And then you continue with if some statement, some code going on. Well, guess what happens? This turns into backslash that gets spliced into the comment, and your very nice statement just evaporates.
I'm not feeling the loss here.
Okay, so very few people know about this, and as a matter of fact, most production quality compilers don't enable trigraphs by default. Our compiler, VC++, has a switch to turn it on. So there's Clang, so there's GCC. Very few compilers actually have this, and it is not a loss.
So it's not unfair for me to say, if you're doing this, you may now, and indeed must now, stop it.
Yes.
Okay.
Except if you're paid to work on these very special systems where you must do this. But for the vast majority of programmers, this is good. It's gone. Good.
All right, good. What else? What else did you guys yank?
So the next thing that went out of the standard is relics from C++ 98. So essentially in C++ 98, the only way you could kind of have automated lifetime management is through auto pointer of T. And we all knew that this type was in the standard, but it was using techniques that we will never want to explain to the working programmer, because they should even know about the tricks that they use to do that. And thankfully for C++ 11, we got unique pointers, shared pointers, and a bunch of other stuff. And unique pointers happen to make auto pointer redundant. So this is a hazard that was in the standard, and now that we have unique pointer in 17, and 14, after 3 years of actual use, we got enough data to take this out of the standard. You should never know about it, and you should never tell anybody to read about it. So I'm not going to tell you how to use this. I'm just going to tell you this doesn't exist anymore. If you feel like you need to use auto pointer, no, don't. Use unique pointer, and you'll be better with it.
All right, so go ahead, go forth and search your code for auto pointer and get ready for the transition.
Exactly, and there are some other stuff like member pointer. Basically things that we had to write in C++ 98 because the language wasn't expressive enough. But thankfully with C++ 11 and 14, we don't need those things anymore. We can write that much better with lambdas. I think now all compilers, including Microsoft compiler, supports lambdas.
Awesome. So we talked about some of the changes to the core language. Now let's take a look at some of the things that have been added to the libraries. You mentioned that there was a first draft of the fundamentals technical specification, and that added string view and array view. Can you tell me about string view?
So string view essentially tries to provide a reference semantics for strings. We know that it's two strings we like, love, and use all the time. String as hello. Now, this is really a fundamental type, and this is where you have to think about it. However, it is very difficult to use it at API boundaries because the representation varies a lot depending on implementations. But there are a lot of APIs, especially some we inherit from C, that requires you to pass strings around. They don't actually modify the strings. What you can do is you can use what we call string view. You can make a string view out of a string. What this does is it creates essentially a reference it provides a view over the string. So here you have a complete view. You can pass it around. You can put it in API because it's really very simple. It doesn't have any surprise. If you read from the view, it reads from the underlying string. If you write to the view, it will write to the underlying view. So the previous specification for the string view only allows you to read from the string, and there is a modification that was voted into the last specification that allows you to actually write to it.
So writable string views are new.
Yes, right, yeah. So, but essentially, you have your data sitting somewhere here, and then you have this view over the string. You can have a complete view, or you can just have a window into the string. And this abstraction has been found to be very useful from in different projects. So internally at Microsoft, we use it. If you talk at Google folks, in Clang project, they use it. In the Chromium, they use it, and they had different names, but for the same abstractions. Here, having a standard name for the same abstraction allows you to talk to peers and
makes the code more portable.
Yeah, yes, and more effective communications.
When do I want to use a string view versus a string?
Very good question. Why do you want to use a string view instead of string? So in general, when you call a function, most functions do not actually want to have a copy of the of your string. For example, if you want to compare strings, you just want to have a reference to it, right? But reference in itself doesn't allow you to have a view, a window into subparts of the string. So if you have large strings and you want to manipulate only parts of the string, that is where you like to have string view. So
it's like an XML reader or a parser or a...
Yeah.
Got it.
You name it. You know, if you're writing compilers like me, you have, big strings and you just want to poke into pieces of it.
So then what's array view?
So array view is a generalization of string. You can think of string view as array view where the type element is char, but it is more general than string. It supports multi-dimensional arrays. If you're doing numerical computation or graphics computation, you really want to use array view.
All right. Moving on from the fundamentals TS, you mentioned that there's the transactional memory.
So this has to do with how we do some form of concurrency. So essentially, imagine you have transaction. You want to do some computation.
Either like a two-phase commit kind of approach.
Yes, it will succeed or fail. If it fails, you want to roll back to the previous state, and if it succeeds, you want to move on. And this is fairly complicated, and I don't know all the details. I just know how to use it when I'm asked to use it.
Okay, cool. And then I think the final TS that you said got brought into the committee was the parallelism one.
Parallelism, yeah. So this is what's behind Parallel-STL, and it has been it has received a lot of contributions from not just Microsoft, but from Bloomberg and NVDA and all.
Okay, it's a real community effort.
I'm actually very excited to have a common way of dealing with concurrency and parallelism.
Great. At this point, if you haven't seen it, our very last episode of Going Native had a introduction to Parallel-STL, and so that's proceeding apace, and we're still looking for any and all feedback that you folks have on using that in your things.
Okay, so there is one core feature that was fixed for C++ 17. It has to do with uniform initialization, right? We want people to write things like vector of int v use brace initializer. So this is C++ 11 feature.
So those are curly braces.
Yes, curly braces. Then we move further. We had automatic deduction of variables. So we want to have variable x. We say x equal 42. The type of initializer is int, and the compiler will deduce x as having type int using the usual template argument deduction rules. But at the same time, we also tell people, well, use the uniform initialization syntax. So if you write in C++ 11, if you write auto and 14, if you write auto x y 42, you'll get a surprise. The surprise is this is no longer considered an int, it is considered an initializer list of int. Because
an initializer list of ints?
Yes. So essentially, the type of this thing will be deduced as stud initializer list of ints. And this has caused endless trouble and discussions. At the last CBPCon, there were long discussions about it, and now it is fixed. We don't want to talk about it anymore, meaning that this y now is no longer initializers of int, it is int.
That is much less surprising.
Yeah. So the good news is this is now implemented by, I think, all the compiler. We had it in C++, in Visual Studio. Was it in preview?
I don't know.
Yeah. Anyway, it'll be there in your next compiler drop, and please continue using braces everywhere.
Great. All right, Gabby, thanks for sharing all that with us. So what's next for the Standards Committee?
Well, the next Standards meeting is in Lenexa, Kansas, early May. And we have a lot of stuff in the pipeline. So at the last Standards meeting, we had more than 129 papers to read. That's that much work. So yeah, we have modules coming. So modules, essentially, this is a way to replace our include header files and scale builds and enable static analysis tools and a bunch of stuff, good stuff that the .NET folks have, for example.
To help you effectively improve things like build time?
Yeah, build time, build throughput. You're going to express the dependencies of your library directly in the source code so that you can have tools that help you with that.
And it'll kind of change the include module,
yes.
include.
So yeah, we're trying to evolve the include model. It will not go away, but it will not be the primary way of organizing your source code.
Oh, interesting. All right, what else?
Today in C++, when you call a function with list of arguments, the order in which the arguments are evaluated is not specified, and that can cause a lot of headache, trouble. There are proposals to fix that. At the last meeting, the committee was very supportive of it, so that's coming for the next year. And on the topic of concurrency, we're going to have support for await. So await is this mechanism that allows you to express concurrency without taking lock or delays and just express the code the way you will naturally write.
Cool. All right, thank you, Gabby.
Hope you guys enjoyed our interview on the up-and-coming in C++ 17, and we will do our best to keep you guys posted on the upcoming developments.
And don't forget to download the Visual Studio Preview and give us all the feedback that you can.